This is problem 17-30. A 2 kilogram package slides on a frictionless floor and strikes the bumpers shown in the figure. The two linear springs are identical, with spring constants of K equal to 1.5 kilonewtons per meter, and the mass of the bumpers may be neglected. If the initial speed of the package is 4 meters per second, determine the maximum deformation of the springs. Okay, so they give us a mass and they give us a velocity for this package. And since in this section, they want us to use the work energy method for analyzing this dynamic system, we are going to talk about and compare the kinetic energy of the box to the final kinetic energy, and then determine the work done by the springs using this method. Okay, and what is asking us for is to determine the max deformation of the springs. So basically, I'm previewing to you that we know everything except for the distance traveled. So let's take a look at this math and see how this works. All right, let's start by visualizing a little bit what's going on here with the free body diagram. And we're going to have, and not always, but we are going to eventually have the force of spring 1 and the force of spring 2 pushing to the left. There will be a normal force, and there's also a center of gravity, 2 times 9.81. All right, so that is the free body diagram for the box, and we know that the spring is going to create some sort of work on the box. So let's set up that equation. So the work of the spring, both springs, is going to be the integral from the beginning to some distance, and the spring constant is going to be negative 1500 x dx, right? However, there are two springs. So let's go ahead and add the second spring in. So 0 to s, and then negative 1500 x dx. However, if we look at the diagram, I'll just draw the diagram over here on the side. There's a first spring and there's a second spring. And in the diagram, they show that there is a distance of 0.1 meters before the box will reach the second spring. So that means that the second spring, spring B2 in the diagram, doesn't actually start doing work onto the box until after the box has moved 0.1 meters, which means the spring will not be doing work for 0.1 meters of the motion. So therefore, since basically work is just the force times the distance in the direction of motion, then the first spring is going to go across the entire range of motion, and the second spring is going to go across a shorter amount of range. Okay, so if we do these two integrals, then we will end up with negative 1500 s squared over 2 minus 1500, and then s minus 0.1, and this is squared, over 2. All right, if we just do the algebra, then we end up with a second degree polynomial that is 750 factored out, 2s squared minus 0.2s plus 0.01, and this is joules. All right, so s is the distance that is traveled by the box as it contacts the first spring, then the second spring, and then stops. Well, this analysis doesn't fully describe that scenario, because how do we know the box stopped? Well, that is where the work energy method will come into play in order to illustrate mathematically that the box is coming to rest. All right, so first we need the kinetic energy that the box has initially, which we should know is 1/2 the mass times the velocity squared. And we have these values. 1/2 times 2 kilograms times the 4 meters per second squared that is given to us, which equals 16 joules. Okay, then if we take the work energy equation, So the initial kinetic energy plus the work done on the object is equal to the final kinetic energy. Then we plug in the values, but what is the final kinetic energy? Well, we are wondering how far the box travels when it comes to rest. So therefore, this final kinetic energy is 0. So we can plug in the 16 joules for the initial kinetic energy, and then we can add the negative 750 times 2s squared minus 0.2s plus 0.01, and this is all equal to 0. And now we can solve for s. All right, well, the final position, s, is 0.1404 meters. All right, and so that means that the spring 1 travels 140.4 millimeters, and the other spring is minus 0.1 of that. So therefore, 40.4 millimeters. S1's distance and S2's distance.